Okay. Hello, everyone. Welcome to MLBBQ. And today I'll be presenting Olympiad Formal Mathematical Reasoning with Reinforcement Learning, also known as the Alpha Proof paper. This talk will be very much out of distribution for the kind of talks that we usually have here at Trends. And so please do uh, stop me and ask questions whenever things get a bit out of hand. So without further ado, let's start. We're going to start a bit in media res and explain the higher level of what is alpha proof. So alpha proof is a paper that was published and accepted, or it was accepted 2 days ago, or it was published 2 days ago. And originally, I was going to present different work from Kimi on the same topic, but because alpha proof is the more, how do I say this, engineering-wise interesting paper, I've decided to pivot to it because it goes into a lot more detail into how they've handled their reinforcement learning pipeline as well as how they handle the specifics of the Lean language. Here is a brief overview of what Alpha Proof is going to be, and we're going to basically cover the specifics of it as we go along. So, question. Oh, Dennis David needs to get on the paper. Yeah, that's true. We're on recording, so I won't make too many comments about that. So the first part is the lean environment itself. We'll cover what is a lean environment or even what is lean. The second part is the proof network. This is where AlphaGo and New Zero and all those things that you're familiar with comes into play. And then the tree search, which there is actually a modification that is designed specifically for the lean language. So here's also a rough sketch of how the training task goes. The first is a translation of a bunch of informal problems into formal problems. And if you note, the number of informal problems is only 1 million, but the number of formal problems is 80 million. And so they're doing a lot of upsampling because there's multiple ways of formalizing the same issue. And then you can use this as the baseline for RL for your proof network plus the search. And then the new invention from this paper is this new thing called test time RL, which only works on a verifiable benchmark or only works on a verifiable baseline, where you take a target problem, a singular target problem. You can use a variant generator and obtain hundreds of thousands of variants of the same problem, and then RL on those. And so you can do RL at test time. This is completely different to the other kinds of quote unquote test time training that other people have attempted. This is a true like actual RL. This is the exact same thing as the core RL loop, but now applied to the already trained network. So TLDR, it is better than all of us at math. Every single person here at Trends, a score, if you look at the last column, Putnam bench. Anyone here know of the Putnam? The Putnam is a yearly math competition for undergraduate math. It covers everything from combinatorics, algebra, calculus, geometry. It is widely considered the hardest math competition in the collegiate level. And the median score, so like it scores, I think, out of 120. Anyone want to guess what the median score is? 70. Zero. The median score for all contestants for this test is zero. And Alpha Proof manages to get a 56.1, which is actually a 67 score on the test. And a 67 score translates to 99.4th percentile on the Putnam test. And given that the Putnam is usually only offered to math undergraduates and also only math undergraduates who are interested in competition math, double selection effect, and even among that, 99.4th percentile. So it's extremely unlikely, and if you look up a Putnam problem, it's extremely hard. And yeah, so it's pretty decently safe to say at competition math, it is better than basically all of us, and that's with 500 TPU days. And we'll get into that later. So yeah, this is a distribution for the Putnam. Most people get like 0 to 1 to 10. And 1 to 10 is a grouping, so the actual biggest category is 0. So what is mathematics? So the history, this is a quote from the paper, the historical arc of mathematics has been one of increasing formalization. We started historically around Euclid with geometry, and Euclid's postulates are basically five assumptions about geometry. If you actually follow through them, they aren't necessarily statements as they are construction rules for geometry. And so it's like the 2 points define only one straight line is telling you how to make a straight line using 2 points. All right angles are equal actually is a way of telling you how to construct right angles, because if you take a line and you bisect it, you create four equal angles, and so on. And so this is the start of it with geometry. Very like loose statements, but it's still grounded in a formal quote unquote way of creating shapes with the tools they had access to at the time. And then al-Khwarizmi, if that sounds familiar, this is what algorithms is. This says algorithms right here. He actually invented algebra. He also, him and his research group invented the Arabic numbers that we love so much, right? He also did a lot of the early work in arithmetic and also looked at polynomial solutions and a lot of algebra. And then Viete is where algebra actually starts. This is where all the notation that we end up using comes up. And so how to compose addition, subtraction, equals, integrand. I'm not sure integrands were invented at this time, but it's like the notation and the style of math that we do today was invented around this time. And then modern mathematics, or start of modern-ish mathematics, Newton and Leibniz with calculus. And then this is where mathematics starts eating the world, and this is where things are starting to condense. Whereas before there was geometry, algebra, and then like all these different math fields are studying kind of different things. Around the time of calculus is where things start coalescing, and it really, really, really kicks up around these two guys. That's David Hilbert, and that's Gödel. And Hilbert had his program. It's called the Hilbert program. It's an attempt to show the true strength of mathematics by turning into a completely formal field, by axiomatizing itself and then proving that the axioms are sound, or proving from those axioms that the system as a whole is sound or consistent. And as Gödel proved eventually, this is impossible. A system cannot prove its own consistency. Even worse, a system cannot prove its soundness. Soundness is even a stronger property than consistency. And any complete system is necessary. So you are left with only sound and incomplete systems, which are systems that are at least logically okay, but logically internally okay, but they can't prove everything. And this is very load bearing later on when we talk about lean, because soundness cannot be proved in the system itself. Which means that if you want to trust a system of mathematics, you actually have to basically put it on blind faith. Like, how do we know that ZFC is sound? We actually don't. We just have seen so far that it's not able to prove contradictions.
So basically, these systems have a very limited scope of things that they can even reach. But there are potentially things beyond these formal systems that exist.
Potentially, but it's unprovable.
Okay.
We know that it's unprovable. So there are claims regarding if we had a way of doing actual real number arithmetic, you can solve the halting problem. There's like variants of these kinds of things, but
what is this problem?
Huh?
What is this problem?
This problem is the problem of mathematical description. Is there a version of mathematics, depending on what axioms or systems you choose, that is able to prove very strong statements like this mathematical system is sound, right? But no system can prove
Or
that.
this statement is true.
Yeah, this statement is true. Or like,
Or this
but so far,
false.
yeah, exactly. That's consistency. Consistency means that it can't prove a statement and its negation. So only one or the other. Soundness is an even stronger claim, which is that you can't prove a contradiction. Yeah. And so far, the best that we can do is sound but incomplete systems. So there's a bunch of things we can't prove. And this birthed essentially modern mathematics, like set theory, and then eventually, this is Bertrand Russell, Russell's paradox, if anyone's heard of it. And he tried to axiomatize and formalize all of mathematics in his 3 books, Principia Mathematica, not to be confused with the other Principia Mathematica by Newton. This one is the book where it took until like page 270 of the first volume for him to prove that 1 + 1 is equal to 2. It's like a lot of machinery for you to be able to get there. But this attempt failed, but it basically spawned the field of computer science. And so now that we have computers, whatever shall we do? So in the realm of formal mathematics, this was still, Principia is a book, and verification of logic in Principia Mathematica is a somewhat linguistic process that requires people to go through. But given that this is a formal system with decidable rules, what if you create a system that could mechanically do that? Like take the symbols and then transfer them into a statement about whether or not the proof is valid in the language. So that's where proof persistence and Lean come in. So Lean is a language made by Leo de Moura, and it's not only the only proof persistence in town. There's also Agda, Holmlight, MetaMath, Isabelle, RockQ, Kind, so on and so forth. There's tons of these, like probably hundreds in history, but these are the ones that survive. And one of the core insights that led to like why turn mathematics into a programming language is the thing called the Curry-Howard correspondence. It's a statement regarding this duality between computer programs and proofs. And they found, Curry and Haskell Curry and Alvin Howard found that there's basically no difference between the two. Specifically, it says that proofs in constructivist logic and programs in simply typed Lambda calculus are exactly dual. So recursion is dual to induction. Functions are dual to implication. Conjunction is dual to conjunction and is dual to a product-like structure in programming, and then sums are dual to an optional structure in programming. And so,
Question.
Yeah.
What is the equivalent of proof by contradiction?
Proof by contradiction is proof by contradiction. Okay, so proof by contradiction is complicated because proof by contradiction, you can't do proof by contradictions in well, you can't always do proof by contradictions in constructivist math because there's this principle called the principle of explosion, and also this thing called the BHK interpretation, which are the axioms, basically the axioms of propositional logic in constructivist math. Not A is not the same as A. And so it's very funky. You can only do it sometimes. So you can still prove statements like √2 is an irrational number, which is usually thought of as a proof by contradiction, right? But if you actually look at the word irrational, it's a statement about it not being rational. And so it's actually a direct proof. So you could, if you assume that √2 is rational, you can then prove a contradiction, right? Which means that the statement has to be false. Which means that √2 cannot be a rational number, which is irrational. But in classical mathematics, the word irrational is thought of as a positive statement. It's a statement about the number. And so the proof of the irrationality of √2 is thought of as a proof by contradiction, but it's actually a direct proof. But there are many more proofs like that. You can't prove that every vector space has a basis in constructivist linear algebra. You can't prove the cardinality of the reals is larger than the cardinality of the naturals in constructivist analysis. There's like many things like this. Yeah. So it's formalized based on this thing called dependent type theory. Anyone here use types? Do you use types in your Python program, Joanne?
No, I haven't used types since like Java.
I see. Yeah, the Java types are also different from these types. Java types are they're like names somewhat that point to a class. So it's like a template for creating an object. A type in this notion is actually dual to a construction law for an object. Like an integer, if you type something as an int, it says something about how that int is constructed and what it can be used for. On an operational level, they're the same thing. Like if you do int plus int, that's fine. Int plus string, who knows? Ints plus float, sometimes it promotes, sometimes doesn't. And so the formal logic of thinking about these interactions is type theory. And an extension to type theory is this theory of dependent types, where the type cannot only be static, it can depend on the value of something else. So think a vector, right? Wouldn't you love it if you never had shape errors in Torch, right? Everything's static, like it technically should be fine. But this requires you to encode the shape in your types. Like A is a tensor of shape n by n, right? And that changes depending on what you plug n in, which means it's dependent. That's what a dependent type is. Dependent types correspond basically to existential and universal quantification in logic. So the upside down and the backwards e.
Can we say that like dependent types, like a scalar as an example of tensor with 0 dimensions or something like that?
Yeah. The tensor, usually in Torch, in like a non-dependently typed language like Python, you can only say that something is of type tensor. If you want to describe it's a tensor of shape something, like extra statements about it, then you need dependent types. Yeah. Or if you wanted to describe a sorted list, you also need to have dependent types, because a sorted list, its definition is dependent on the construction of the list itself, like the underlying list. You have to define it inductively as like a list where every element is, say, like less than the element right next to it, right? And yeah, like it's a very general language. If you programmed in Rust before, also you can also see that you can embed very very rich semantics at the type level, and this is very good for programming. But it also happens to let you describe basically all of mathematics with it. And so, for example, here's all of set theory. This is every single axiom of set theory in one single screenshot. It's from Terry Tao's analysis book, Formalized to Lean. Yeah, it's extremely dense. It takes like 20 pages to go through that. But as an example of the kinds of proofs that you can do with Lean, this is a trivial example. The statement Q and P implies P and Q. And the way you would write this in Lean is like that. Example is a way of declaring an unnamed theorem. P and Q are propositions. So propositions are things that can inhabit true or false. H is the hypothesis, which is the thing on the left, which says that Q and P, and the colon over there says this whole proof has the type P and Q, right? And then the walrus right there says that this is now we are entering the proof of the statement. And on the right, this is where Lean has its superpowers. This is in VS Code, and if you have the Lean extension installed, it will actually give you information about the theorem that you're proving. And so if you have the line highlighted, it says that there's one goal. You currently have the information on the top, like in yellow. P and Q are propositions. The hypothesis is that P and Q is true. That like sideways T is read turnstile, but I read it as entails. So the yellow stuff entails that P and Q. So the way you would prove it is first, you apply the introduction law for AND. When you apply AND intro, you're splitting the statement P and Q into two different proofs. The first thing you have to prove is P is true. And the second thing you have to prove is Q is true, which is trivially like easy to see how this is the same thing as proving that P and Q, right? And then, this is, now, since it's two cases, you have to do case analysis. That dot right there is pointing you to the first case. So the first case here is you have to prove P. And you can prove P by selecting H dot right. So the right side of the hypothesis right there. So it says P and Q. So the P, Q and P. So the right side of it is P. And then you do the same thing for left. And then Lean will tell you that goal is accomplished. So this is how you prove a statement in Lean. And you can now go on and prove everything else in propositional logic. You can prove everything you want in number like natural number theory. You can do everything in analysis and so on and so forth. It's a very generic, powerful language. So
can I try to summarize it? So like to prove that A and B equals B and A, they prove that if A and B is true, then A is true.
Right, because you can always do reduction. Yeah, this is called the weakening law of conjunction. So A and B implies both A, but it also implies B. So you can always extract out one of the two. Yeah. And then you can use A to show A trivially, and then you can use B to show B trivially. So in short, Lean is a functional programming language like Haskell. It's also a language for writing proofs. It's also a system which can validate proofs, which is extremely powerful, with scaling considerations for automation, amenable to programmatic use, which will come into handy later, such as an RL environment. So MATLib, this is one of the largest, as of the writing, largest attempts to formalize mathematics in basically any proof-resistant language. This is MATLib. MATLib has some multiple versions. This is MATLib 4, which is the MATLib for Lean 4. It contains 210,000 theorems and 100,000 definitions, and this spans like almost everything you might see in undergraduate mathematics. You want analysis, you want algebra, you want category theory, you want abstract algebra, you want analysis, you want geometry. I think there's even algebraic geometry in there. Like everything from undergraduate to even some graduate mathematics is included in here. And it's massive. It's like over a gigabyte. As for the question of why do mathematicians specifically care about Lean? Because these tools were originally only used and cared for by people in computer science. It got born out of the world of formal computer science independent type theory. Well, the reason is that Lean was designed from scratch with mathematicians in mind, and they managed to pull quite a few mathematicians on board through experiments like the liquid tensor experiment, which is far and above my pay grade to explain what the hell it's about, but it's basically it's at the frontier of what people are doing with mathematics. Peter Scholl's right there is a fields medalist, and the liquid tensor proof is one of his most proud works. He was more proud of it than he was of his Fields Medal winning proof. And so it's the peak of like the hardest math you could reasonably have to do as a mathematician. And the fact that this could be done in Lean was a case experiment for the fact that Lean could handle such a large project. It was a pretty massive project of a couple hundred theorems. And it was handled by this guy, Kevin Buzzard, great guy. He also made this thing called the natural numbers game, which is a tutorial for Lean. And ever since then, more people have joined this ecosystem. For example, Terence Tao, widely considered one of the greatest mathematicians alive, possibly the greatest mathematician alive. And here he is using Lean. And even funnily enough, he's using Lean in conjunction with LLMs. Like while the LLMs aren't good enough to replace him, they are definitely better than him at Lean. They're way better at like the reasoning in Lean syntax and how to use the Lean tooling and crafting theorems and proofs using those tools. And so he heavily uses LLMs in his work to formalize things. Yeah, and he also has a couple of talks regarding it, both machine-assisted proofs and also AI-assisted proofs. So, a case example, the prime number theorem. The prime number theorem is a statement regarding the distribution of primes in some amount x. So pi here is the number of primes in some number of natural numbers x. And that distribution is x over log x. Very simple statement. You would think that this is easy to prove. It is in fact not easy to prove. This is from the strong prime number theorem proof done by Math Inc., where I was a contributor to this project. And this is every single one of those green bubbles is a theorem. If you zoom in 100x, like at the top over there, you can see each and every one of these. This is the dependency tree for the theorem. And at the very, very bottom here, that's the prime number theorem.
So there is an associated Lean program to this entire map.
Yes, it's 6,000 lines of Lean. And this is the dependency tree for that program. It's completely massive. Same thing here. This is the graph of the liquid tensor experiment. I think this is pretty zoomed in, but yeah, it's also pretty massive. And so it would start out as completely white. White means not formalized. And then blue means that it's been formalized but not proven. And then green means that it's fully proven. And so there is this cool thing happening where bubbles would just start filling in with new colors. And because the entire system is verified, you actually didn't have to care. You can just prove the statement. locally without having to care about why you're proving it or what it's used for. Because everything, if it compiles, it'll lock into place and you can use it. And so this enabled dozens and dozens of contributors to contribute to this one project.
So do people construct these graphs first and then try to prove little parts of it?
Usually, yeah, usually. Usually it's the head mathematician on the project. In this case, it was Peter Schultz himself who constructed the blueprint, and then Kevin Buzzard translated the same blueprint over to Lean, and then that's how this graph was constructed. And then the graph would go through iterations. For example, if someone proved halfway through a statement, but he had to spawn a couple of lemmas, then there would blow up some more lemmas. So that's also what happened over here. Originally, you would start with like a very small scaffolding of maybe 20, 30 bubbles, and then the more you fill in, it blows up, and then it blows up even more. And so, yeah, in conclusion, Lean is strong and efficient enough to handle frontier math. It has garnered enough attention and work for some big players like Terry Tao and Alex Kantorovich. It has proven to work at scale for extremely large, 6,000 lines of code would translate to like 100 pages of math proofs. It's a lot, even potentially even more. It has strong community backing from both the computer science, machine learning, and also the mathematics community. It is also used by big players like Google, Microsoft, Amazon, and it is an adaptation of the hit like very old video game mathematics. So now we enter alpha proof. Okay, so now we know what Lean is. What is a Lean environment? Right? A Lean environment required lots and lots of manual labor because it's still a programming language. While you might have things like basic propositional logic, you might not have utilities like converting or extracting out the numerator from 3 over 4, like 3 over 4 down to 3. It was not there. And so Google DeepMind had to write those utilities themselves. And so this is where it shows that you need actual Lean expertise. So people not only good at math, but also good at math infrastructure. So you need software engineers to handle it. You also needed a bunch of custom handling for scaling concerns. For example, Lean was not designed to be an RL environment, same as Python, and so you would have to put wrappers around it, for example, for handling parallel execution and state management. DeepMind's actually much more careful about it than the average Lean, like Lean for RL user, because they also not only handle the whole proof compilation, they also handle individual proof states. And so back at the PNQ example, every single line that you add in actually changes the proof state, which had a different string. And so when you're doing the export, you have to export for every single line, maybe actually every single character that you put in, because all of those things have different proof states. Then they would have a pipeline for tactic validation and execution. Here's the interesting part. Goal decomposition. Because unlike in Python, where if you attempt to split a task into two, I mean, in most languages, if you attempt to split a task into two, it's unclear if doing both of those tasks completed the original task. Like if I had a project and it had two components, I give one component to one person, give the other component to the other person. Likelihood of them being done with it, the task being done when both of them are done, are basically 0. But in Lean, that's not true. In Lean, if you split P and Q into P and then Q, and you prove both P and Q, you're done. You're done. You're completely done. And so that allows for much more robust code decomposition. And an interesting thing that the alpha proof does that hasn't been clarified before is that in addition to attempting to prove the statement, they also attempt to prove its negation. And so they prove both the statement and its negation, which in the variant of Lean logic that they're using is actually fine. If you accept the law of excluded middle. So back to your point of proof by contradiction, if you accept the law of excluded middle, you can actually do either A or not A. And then only those two things exist. Yeah. And then turning Lean into an RL environment proved to be a engineering challenge of its own. So you have to consider, does it run fast? And so they had to compile some components like the linarith tactic into C, and this made it run 6 times faster. They also had to consider, okay, what if the proofs take way too long? And so they had to implement a wall clock time limit. They also had to implement a bunch of system check tooling to monitor the verification process to see if anything needs more resources, see if things are going to die, and so on and so forth. They also had to modify the multi-precision integer library in Lean. So in Lean, integers aren't just like I32, they're actually I basically infinity. There's no biggest integer in mathematics, and so it makes no sense to have a biggest integer in Lean. Yeah, and so even after that, they also had to do an independent final check for the proofs. And so in addition to checking the proofs on their harness, they also have to port that over to the core regular Lean modules and then check it over there. And so incredible care has been put in place to make complete sure that if the proofs are outputted by the LLM and the system says it's correct, it's actually correct. Okay, so now that we're done with the Lean stuff, let's look at pre-training and SFT handle. The huge part. It's a 3 billion parameter model. That's tiny. That's tiny compared to GPT-4. GPT-4. Anyone know how big GPT-4 is? It's nearly 2 trillion parameters. And GPT-4 is garbage at formal theorem proving. And so the fact that you can do alpha proof, which gets silver, nearly gold on the IMO with only 3 billion parameters, is extremely promising for all of us. That means that you can probably eventually run one of these things at home. Okay, this is a full transformer, full encoder decoder transformer, so it's not exactly a GPT. It's consistent with the architecture that they used to do alpha code, which is a different paper. SST data. I covered this a little bit before, but they use an auto-formalization system. In this case, it's basically just Gemini Pro 1.5. So this is not end-to-end trained, and this could definitely be a work in the future. So they translate a problem like that. Let n greater or equal to 2 be an integer, and let a1 through an be positive real numbers with some 1. Prove that arithmetic bound. And then you would plug that through the formalization system into that theorem in Lean, right? Importantly though, because things in Lean, once they're proven, they're definitely proven. It doesn't completely matter that formalized statement does not correspond to the original statement, at least for the purposes of pre-training and SFT. Because if it's proven, it is proven. All right, it doesn't matter. We're only training for exact provability, and so it's actually somewhat of a benefit that it doesn't translate it fully honestly, because this means that you can upsample. You can sample this multiple times and get slightly different problems every time, which means that you have a much wider data set, like slight variations. You can think of it as kind of a way of doing regularization, but in proof space as opposed to latent space. So now you have a bunch of randomizations or like perturbations in the data set without having to explicitly encode for that. So thank you, Gemini 1.5. They also use a large pre-trained data set, unclarified where it's actually from, but they say it's publicly available code and mathematical texts. They do next token prediction, so it's kind of a GPT. And then the encoder process 1.12 trillion tokens, while the decoder reconstructed 3 trillion, so roughly 50 epochs. And then they also do SFT. SFT was on the specialized corpus of state tactic pairs. So in addition to the auto-formalized problems, they also had a bunch of collected state and or collected Lean code and the Lean state pairs. So having the model predict the state allowed it to understand the states of the Lean program more and understand its internals more. Because if you only train on Lean code, you actually have no idea what's going on under the hood. So much of Lean is actually just staring at the Lean info window. And so if you don't train on Lean info window, you're actually missing about half a picture, if not more. Okay, so, and then you also have tree search. This time, not necessarily Monte Carlo, because Lean has this very fancy conjunctive branching that is atomic and also sometimes necessary. So unlike a regular Monte Carlo tree search, like in AlphaGo, the system does not only branch when it thinks it should branch, it sometimes has to branch. if the proof step gave you a P and Q, you kind of have to split up the case and then independently prove P and Q, which means that now it's in addition to the regular Monte Carlo tree search for the purposes of sampling, you also have tree search for the purposes of exploring the proof search space. And so it's doubly tree search. And then here are some details for how they did the weighting. It's a modified version of the MCTS function that they used for AlphaGo. And here are some specifics for like how the information is progressed. In addition to, what's it called? In addition to only handling the sampling process within the tree expansion, they also do this thing called progressive sampling. And this is interesting. So they actually handle the case where, how do I say this? They basically upsample areas where the simulation is, or they downsample areas where the simulation has crossed that path multiple times, because the model can actually reach the same proof state through multiple different paths if you're in the same theorem. Because you might think, you might find that a certain statement proves its companion. For example, if you P and Q is related to some way to P, then if you're down the path of P, you might already have proven something related for Q. And so because you can have the global view of the whole tree, you can actually take that information into account for how you sample or how you allocate the tree budget. And so there's a much more fancy algorithm than just mundane Monte Carlo tree search. So, reinforcement learning. This is pre-training reinforcement learning. This is how they pose the problem. The state represents a complete logical context within the lead prover at a given step t of a proof attempt, encompassing all active hypotheses and remaining goals. This is basically the most recent line in lead, plus all the information preceding it. The observation. So the agent observes a state as a pre-printed string representation of the lead tactic state. That's the lead info window. Action. An action is a lead tactic. A tactic is basically just a small program to modify state. So we saw in the example for P and Q, apply and dot intro is a tactic. It's a way of applying the tactic called and dot intro, which splits up P and Q into two proofs, one for P and one for Q. Transition. Transitioning means applying an action A, which is a tactic, to the state, which is the program, and you use the lean environment to execute that tactic. So you execute that small program, which returns, well, actually, before that, if the tactic is actually correct and valid, then lean will new state, which is the program, plus a tactic, and a new state, which is the lean info window at that point. Right? The episode is the entire math proof, and the proof terminates when the proof is completed. So the model found the proof, or a compute budget is exhausted. So there's multiple different budgets. There's a budget for the model inferencing. There's a budget for the tree search. There's a budget for lean. So if any of these exhaust, the proof is terminated. The reward signal. So interestingly, they actually incentivize the discovery of the shortest proof. So they apply a negative reward for each tactic applied. So they have a ceiling. They have a undeclared ceiling reward for the whole proof itself, and then every tactic you use, you subtract one from the reward.
So for a given problem, there's a number of different tactics that you could use to try to branch off it and prove a part of it.
Yeah.
This is exploring all of those.
All of those. Yep. You can do multiple time sampling. This is more useful in training time than it is at inferencing time, because at inferencing time, you only care about the first proof. But at training time, you actually care about the best proof, because this is the learning mechanism that you're going to be using. Yeah, and then the return definition, the return GT from state ST, it's a sum of rewards until termination. And so sum in this case doesn't mean good, it actually means bad. You sum up the costs of all of the tactics that you used. For states that decompose into multiple independent sub-goals, see and nodes and so on, the return is actually the minimum return, corresponding to the longest or hardest proof among its constituent subgoals. So this means that it can't reward hack as easily, because If instead it is the maximum return, you can see a scenario in which the model just like decomposes into random tasks and then tries to prove like hack the hardest metric by using a bunch of like dumb tactics over and over and over across all the branches. And so to minimize that, they basically say, okay, whatever you do, make sure that even for the longest proof that you do, make that very short. And so that's why they use the minimum among all the branches. This definition recursively applies to ancestor states of each multiple subgoals as a natural alternative. Our choice of the minimum return provides an interesting incentive as it encourages the agent to split goals into subgoals to balance difficulty. Interestingly, though, in combination with the test time reinforcement learning technique that they use later on, this creates a very interesting dynamic. There's no split between pre-training and test time anymore, right? Because now you can think of the model as not only the pre-trained model, but the instance of the model that's currently on a proof on some proof path. Like the model is this is actually it's sounding to me like a version of continual learning, because now the model is being updated along with the exploration. And it's no longer just a matter of applying a pre-trained RL model to some task. That's what New Zero was. But now, because the dynamics of the game changed so much while you're doing the task, you can actually do something like, imagine if you task the model with proving the Riemann hypothesis, right? And it can't zero shot it, but what it can do is generate permutations of the Riemann hypothesis, maybe generating an easier case, an easier bound for the Riemann hypothesis, and then it can try to prove those. And then it can try to prove easier versions of those, and easier version of those. And then it can recursively do this all the way until it only has easy problems to prove. And it can prove those problems. And it's doing RL while it's proving these problems. And it progresses through this tree by proving all these different problems. And this is a very, very promising approach. Scaling curves. So these are 3 scaling curves. First one is performance on the training set. The training set is that 80 million formalized statements. So statements from the start are all undecided and not proven. And then because they try to prove both a statement and its negation, they have this curve for either proving or disproving a statement. So you see that this curve follows another logarithmic scaling law. So one more scaling law. Second scaling law, performance on held up benchmarks. So the 3 benchmarks they use are mini F to F. They use a fixed version of mini F to F. I believe this is the 3rd fixed version of mini F to F. There's been multiple because the original mini F to F translation was done not super carefully by OpenAI, and then Facebook research fixed it, and then now Google is fixing it again. They introduced a new benchmark called formal IMO. It is hand translated problems from the IMO. The International Math Olympiad. And then they also translate a bunch of problems into this benchmark called Putnam Bench. Putnam is done on paper, and you need a team of experts to translate it authentically into lead. And so you also see a scaling law. I'm surprised that they didn't, because those scaling laws for formal IMO and Putnam Bench don't seem to have saturated. So I'm surprised they didn't scale even more. Interestingly, too, not only are the success rates increasing with respect to days of training, you also get more efficient proving. So the 3rd one shows that the model trends towards what's it called? It trends towards finding the proof with fewer attempts. This is kind of like a rotated and flipped log scaling law. If you like flip the y-axis on its end and then flip the x and y axis, you see a logarithmic curve. So it logarithmically finds shorter and shorter proofs as you train it more and more. Okay, so even more curves. You also have scaling of search. So there's multiple scaling curves. You also have these scaling of search, which is the budget that you allocate to your tree search. So this previous slide was compute allocated to the RL training, and this is for tree search and also TTRL, test time RL. And you can see even more sigmoids or even more log scaling curves. And it's kind of difficult to convey like the importance of these curves because every additional problem in the Putnam, given that the median score is a 0, every additional problem is actually like probably a doubling in the skill of a mathematician, basically. Like it's an incredibly hard benchmark, and so it's difficult to say that this is truly like a logarithmic scaling curve because if you imagine like the extra amount of skill required to solve an additional task, it's just insane. Okay, so now to the meat, test time URL. Essentially, what you do is the same thing as you were doing in the auto formalization slide. So you take a problem. Where is that slide? This is so far away. Here. Yeah. So same way. You take a problem, you translate it into lean. But even interestingly, you can take the same lean problem, and then you can translate the lean problem into more problems. So you can turn it into a simplified version of the problem. Again, because it's a simplification, you don't necessarily even have to do it authentically. Because so long as it looks the same, and you can hope that it kind of is teaching you to prove the same thing, you're fine. You can generate multiple candidate simplifications for this for the original theorem, and then you can also synthesize lemmas. So you might take that theorem, and then you can synthesize, okay, what statements are necessary for proving this proof, and then you prove it, right? And then during the proof, you can also discover new lemmas. And then you can repeat this. Like you can recursively repeat this until you run into a problem that you can atomically prove. But interestingly, throughout this process, you've also generated a bunch of problems, which means that you can RL on them. Yay! And so you get another sigmoid, or you get another logarithmic scaling curve, which is incredibly impressive. And from DeepMind themselves, they tell us that they can generate 400,000 different variants for the same problem.
I have a question.
Yes.
Is this branching also happening at test time, or is it only for training?
Both.
Okay.
Yeah, right. Both. It's just interesting. I think it matters less so for the training time because there's so much more data at the level of the at this training time. You already have 80 million problems. You don't necessarily have to do the variant generation, but I can definitely see it being very nice to have. In addition, because they were using Gemini 1.5, Gemini 1.5 is a very expensive model to train. It's probably over 1 trillion parameters, who knows. If they instead train like a dedicated auto formalization engine that could do the same task as Gemini but do it way faster, you can definitely integrate it into the RL loop. And maybe you could now you can turn it into maybe like a GAN style problem where the auto formalizer is trying to come up with variants that are difficult or rewarding for the model to prove. Like that balancing game of like what problem should I hand to you that makes you learn but also is not super easy. And so yeah, there's like so much interesting like future work that can be done based on this idea alone. So cost. If you look, TPU min, TPU hours, TPU days. This is on the V6E TPU, which at a 3-year long contract would cost you about 55 cents per TPU hour. Therefore, 500 TPU days for at the price of 0.55 cents, or no, $0.55, I believe translates to about $6,200. I did this math yesterday. So about $6,000 per problem. That's pretty expensive, but it's pretty insignificant in the scale at the scale of Google, and especially if you're trying to prove a problem as hard as say Putnam, because mathematician hours are also really, really expensive, and it also requires human hours. Here, you only have to put in dollars, and then you get out the proof, which is like so nice. Like imagine if you had a programming problem. It's just pay to win. You just put in money, and out comes the solution. This is also why I'm advocating for what's it called? Advocating for the increased use of lean in general software engineering, because this means that you can turn very hard software tasks into extremely tractable problems of just energy and compute scaling. It's very easy. We know how to scale energy, right? The $0.55 is only because the electricity is costing that much, plus some like cost of maintenance and cost of ownership for the hardware. If you make making chips cheaper and you make making energy cheaper, you've made math cheaper. Interesting, lovely. And so, yeah, and there's so many different axes to optimize this problem on because this 500 CPU days is shared across both the model inferencing, the test time RL, and then all that branching, right? And so, like, you optimize any of these axes and it just like completely chops down on the cost. And so you definitely see this reducing the cost of the end-to-end generation task a lot more in the future. And so far, this is one of the only solutions we have for doing this kind of thing. Most methods that are doing end-to-end formal theorem improving are in the neural domain. People have tried doing this in the purely like symbolic domain, but it doesn't work that well. For example, like sat solvers. You use sat solvers. I mean, Selene uses a whatchamacallit? Selene uses a thing that's similar to a sat solver. Huh?
Like answer set programming.
Yeah, answer set programming. Yes, answer set programming is a subset of SMT solving. So, but the thing is, even though SMT solvers are very powerful, they can't even prove something as simple as integer addition commutativity. Right? They can't prove statements as simple as that, but an LLM can do that trivially. And so, comments. Yeah, it's a programming. Yeah. And so, even though it's kind of lossy, the process of search for in the proof search space, it's so wide that we kind of don't know how to do it without doing a heuristic neural method, which is kind of ugly, but I think works out fine in the end.
For stat solving or
for theorem proving.
oh, okay.
Yeah. Okay, the results. State of the art on everything. Mini F to F used to be completely unsaturated. Now it's completely saturated. 99.6 is about as saturated as you can possibly get on that data set. Formal IMO, they just introduced it. It's already 60% done. Platinum Bench, extremely hard. They're already 50% of the way through. The other two competitors in this game, the big ones, after IMO 2024 is Kimina Prover Preview and DeepSeek Prover V2. Kimina Prover is the best open source one, or the second best open source one. It's very small. It's like only a 7 billion parameter model, and they only get like 1.6% on Python Bench. Unfortunate. DeepSeek Prover V2, giant models. I think 70 billion or 70 billion or larger. Also very bad on Python Bench. These are incredibly hard problems. And AlphaProof just slays it. So very, very nice. Congratulations to Google DeepMind. This is their performance on the IMO. They were 1 point away from a gold. 30. So yeah, they solved all of the algebra problems. And caveat, it was not only AlphaProof that got them a silver in the IMO. They also had this different system called Alpha Geometry, which is interestingly enough not even an LLM method at all. It's a completely different thing. So Alpha Geometry is the one that solved the geometry problems P4. And so in combination, they have the AlphaProof plus Alpha Geometry and placed silver. They have since placed gold with Gemini. So if you want to read the proofs are available online. They're incredibly dense. This is problem one. Problem one is not the hardest problem. And they are largely basically no human would actually write proofs like this. It's very strange, but it works out just fine, interestingly enough. Even better, this one is not done on Lean. This one is done in informal math. And so it kind of goes to show that you don't necessarily need a formal harness to be able to make LLMs do math in a rigorous manner. You can actually bootstrap it off of the formal version and then back translate it into the informal version. Very interesting stuff. In addition, I forgot to add this slide. Okay, so that somewhat concludes our talk. Wow, we're just in time. So any questions? We also have a few questions. Online people also, if you have any questions, don't be shy. It's solved. Yeah. Mathematics is not solved. It's not solved at all. There is many holes in mathematics that have not been able to fill in, and currently they've only been able to fill this in for largely undergraduate level math. The IMO is somewhat, it's explicitly a pre-collegiate competition. So it's only advanced high school to undergraduate style math. To my knowledge, there's been no like actual complete frontier work in terms of like novel fields of math done by LLMs. There has been work at the frontier level done by Math Inc., where I collaborated on of solving or formalizing the strong PNT problem. But that is still in the domain of formalization and not theorem proving from scratch. So that will be the next step. Okay. Any other questions? Okay, that's just the time. Wonderful. Thank you so much, everyone, for joining this. Yeah, thank you. Thank you so much for joining this version of MLBBQ. I know this is kind of disjoint from the kind of materials that are usually collected. Thank you, TJ. Thank you, Sergey. Thank you, everyone online, for joining.
Thank you.
Thanks, Aline. Okay. This down. It was recording, yeah. Yeah, Sergey's recording. It's good. Here we go.